comparison tests and the use of those. Okay, so I've got a few more examples here which we can talk through, and then if there's any other questions or queries or things you want to know about, or things you'd like to talk about, there should be space in the second half of this lecture to ask those questions. Is everybody clear on the arrangements of the test, though? Yeah? Good. Okay, so we'll go through some more examples. Some more examples of the standard and limit comparison tests. I'll bring those up on the board now. So these are convergence tests for a series. When you apply them to a particular series, given series, a series under question, they may tell you that that series converges or that it diverges. If you bring up the in-class test handout, which is up there beside the mock test in the middle page, this is what you'll have in the test. See, this does list the statements of all these convergence tests. So you have there the standard comparison test and the limit comparison test. Now, I spoke about these yesterday as well. These work by comparing the series you're testing. So in this statement over here, the series that we're testing is the series sum of AM. And you compare the series sum of AM to a series that you know about. When I say know about, means you know the convergence status of, whether it converges or diverges. And basically, really quickly, you make a comparison from the series you're testing to a series you know about. If you do the comparison in the right way, then the series you're testing has the same behavior as the one you compared it to. It will either diverge like the one you compared it to, or it'll converge like the one you compared it to, depending on whether you compared it to a convergent one or a divergent. Now, I said if you compared it in the right way, the comparison is slightly different depending on whether you're comparing to a convergent series or a divergent series. It's technical, and you have to do it in the right way. So first of all, the standard comparison test works by setting up an inequality. Okay? Inequality between the terms of your series and the terms of the series you're testing. So recall a series sum of dm. So just to give a brief explanation or a motivation, or a way to think about it, which is helpful. A series sum of dm diverges when the dm do not converge to zero fast enough. Or do not converge to zero at all. It's a little bit difficult when explaining these tests without kind of explaining everything to do with series all over again, because this being mathematics, everything's connected to everything else and it all builds on top of each other. But you recall back to the general term test. The general term test said a necessary condition for a series to converge was that the terms of the series have to converge to zero. So if the terms of dm do not converge to zero, it doesn't have a hope, any hope at all of converging. The terms have to converge to zero, and they have to do so at a certain speed, fast enough. If they do not converge to zero fast enough, then it will not converge. So that's one way of describing why a series fails to converge, because either the terms do not converge to zero, or they do not do, or they might converge to zero, but they don't do so fast enough. Whereas a series, and I'm fitting in here with the terminology which is used in the statements of the tests, series Cm will converge when the Cm tends to zero, as m tends to infinity, and I'll put in quotes here because when they do so fast enough. Okay? So converging to zero is a necessary condition. The terms converging to zero is necessary for convergence. It's not enough. Okay, so the really important example of the harmonic series shows that it's not enough that the terms converge to zero. They have to do so kind of basically faster than the harmonic series, faster than the terms of the harmonic series converging to zero. Okay. So, okay, I'm explaining the standard comparison test here, so let's get to it. So, if we can set up an inequality like this, then this says that the AM behaves worse than, or no better than, the DM. Okay? Bigger than the DM. Things being big leads to divergence. So if the sum of DM diverges and you have an inequality like this, then that will mean that the sum of AM converges. So if you have this for all M, then this says the AM behaves worse than DM, so if the sum of DM diverges, that will imply that the sum of AM diverges also. Okay? If something is diverging and the thing under examination behaves even worse than that, then that will diverge also. So that's one part of the standard comparison test that leads to a conclusion of divergence. The other part leads to a conclusion of convergence, and this is when you show the terms under examination are less than the terms you know about. Okay? And this says, kind of intuitive explanation of it, this says that the AM behaves better than CM. In the context of convergence, this is showing that the terms AM behave better than the terms CM because they're smaller. And when things are small enough and you add them up in the series, converging to zero fast enough, they're small enough, then the series can converge. So if AM is less than CM, this says AM behaves better than CM, and so if the sum of CM converges, this will imply that the sum of AM converges also. Okay, that's the second statement given by the standard comparison. Okay, I've got some examples to talk through now in a moment. The limit comparison test works in a similar way. Sorry, no, works in a different way, but it does a similar thing. You're still making a comparison to a series that you know the behavior of. The limit comparison test, maybe I won't say more about it on the page, but you do the comparison that's shown there. You divide the terms of the series you're looking at by the terms of the known series. So you form that ratio, and then you look at the limiting state of that ratio, the limiting value of that ratio. And if that ratio has a limit, which we call L here, well, what that means is, in the long run, after enough time has passed, after you look far enough down the sequence of terms of the series, the term under question is behaving approximately like L times the term you're comparing it to. AM, in the first instance, AM would be approximately L times CM. You go far out along the series. Or if we form the ratio of DM, AM would be approximately L times CM. And so if the series under question is behaving approximately like a fixed constant multiple of the L, fixed constant multiple L of a series that you know about, then it will have the same behavior as the series you compared it to. Series you compared it to converges, so the one you're looking at. diverges. Note though, there's a slight difference to the way 0 is treated. A limit L of 0 still works if you're comparing to convergent series, but if the limit L is 0 when you're comparing to a divergent series, then you can't draw any conclusion. That doesn't lead to a conclusion of divergence. Okay, let's go through a few examples, and then I'll take. Are there any questions at the moment? First of all. Okay, well, let's go into the examples, and if that causes any questions or queries in your minds, please feel free to shout them out. Okay. So, examples. So the first one we're going to look at is we're going to consider the sum from n equals 1 to infinity of 1 over n to the power n. So in other words, this looks like 1 plus 1 over 2 squared, 1 over 4, plus 1 over 3 cubed, 1 over 27, plus 1 over 4 to the power of 4. Oh my god, what's 4 to the power of 4? 16 by 16, whatever that is. 156, maybe? Whatever it is. Okay. Any guesses about convergence or divergence, first of all? Educated guesses, any feelings about it? Sorry?
Divergence.
Big divergence. Any other thoughts? Why converges? Or? You change your mind? Yeah. Okay. I thought. Well, that's a good illustration of it. So the terms certainly are converging to 0. Okay, so it's 1 over something which is getting large. The terms are converging to 0. So it passes it might converge. It doesn't obviously diverge. Just the simple fact that terms are converging to 0 doesn't guarantee convergence. However, since it's n to the power n, that is really quite fast convergence to 0 compared to 1 over n, say, harmonic series, or even 1 over n squared and so on. It's still going to 0 quite a lot, quite fast, okay? So this seems like quite fast convergence. Quite fast convergence to 0 of the term 1 over n to the power n. So we'll look to make a comparison with the series we know about. Okay. So we'll try to compare to a series we know about. Now, all these terms are certainly bigger than 0. So here's the nth one. It's 1 over n to the power n. So you have n copies of n in the denominator. They're all multiplied together. Well, one thing we could do is compare this by saying, well, let's replace all of those n's by something smaller. Remember, since we're trying to get since we think it might be convergence for the series, we have to show that our term is less than a term of something that does converge. So if I replace each of these, if I replace each of those n's by a 2, well, as long as n is bigger, as long as I'm past the first couple of terms, as long as n is bigger than 2, n times, or n copies, as long as n is bigger than 2, see, I'll have made the denominator smaller. And if you make the denominator smaller, you make the fraction larger. So this will be strictly less than. And this will hold, this will be for every n strictly bigger than 2. Remember, convergence or divergence for a series is determined by what happens in the tail of the series. It's not affected by what happens in any finite initial part of the series. Convergence or divergence is determined by what happens in the infinite tail of the series. So if I forget about the first few terms, this inequality holds. And of course, this is equal to 1 over 2 to the power n. Now, does this look like a term that we know about, say, from elsewhere or using other results? So what is the status? What is the behavior of the sum of 1 over 2 to the power n from n equals 1 to 2? If we can say that this is convergent, then the comparison test will tell us that the series we're looking at converges also. Okay. So how do we know that this converges? What tells it? What kind of thing is it? Geometric. Yeah, this is an example of a geometric series, which the way we wrote it out, we wrote it like this. This has initial term a half, and then common ratio of a half as well. This is a geometric series. Sum of a r to the n minus 1, n equals 1 to infinity, with the absolute value of r strictly less than 1, because r is a half here. So the sum of this a times r to the n minus 1, this is going to have infinite sum, so it's, this is going to have sum 1. Yeah. Remember, the formula was a over 1 minus r. So this is our a being a half over 1 minus r, so 1 minus a half is a half. So this is convergent. So therefore, we've taken the terms from the term from our series under question. We've shown that it's less than the term of another series, and this other series we know to be convergent through the geometric test. Okay, so by comparison with this, we know that the sum of 1 over n to the power n from n equals 1 to infinity, that this also converges. Okay. Doesn't tell you what it converges to, although it probably tells you it converges to something less than 1. Although you might have to shift it up or down depending on the first couple of terms, because I only consider this for n bigger than 2. But it converges, it's something fairly small it converges to. But we know that it converges. Okay, any questions about that? It's kind of good because I brought in the geometric test as well. Okay, let's look at another example. Here we're going to consider the series sum from n equals 1 to infinity, n squared plus 1 over n cubed plus 1. So when n is 1, this is 1. When n is 2, this is 4 plus 1, 5 over 9. When n is 3, this is 10 over 28, so on. What are these terms doing as n gets larger and larger? What are the terms of the series doing? These also look like they're converging to 0, because you've got an n squared divided by n cubed. Well, the n cubed is going to be getting bigger and bigger and bigger faster than the n squared. These terms are going to converge to 0. So you could say it isn't obviously divergent. It passes, or it passes the general term test. The general term test does not say that it is certain that it is divergent. It could still be divergent. Now, anyone like this, any series like this that is a rational function, a rational function of the summation index, so n is the summation index here. And so a rational function is a quotient of polynomials. Remember from our work in chapter 3. Any series like this can normally be tackled using the limit comparison test. It can normally be handled using the limit comparison test. It's a good rule of thumb. The only thing is, what do you compare it to? So there's the limit comparison test. You can either try and compare it to a convergent thing or a divergent thing. We form the ratio, we take the limit. But we have to know what it is we're comparing it to. And the way you work that out normally is you look at the dominant behavior. Dominant behavior of the term, which I look at the quotient of the leading terms. So if in the general situation with a quotient of polynomials, okay, there could be lots of stuff in polynomial on top, lots of stuff in the polynomial on the bottom. But just look at the leading term, the dominant term in each one. So the dominant term in the numerator here is an n squared. The dominant term in the denominator is an n cubed. Look at the ratio of those two. It's 1 over n. So the feeling you get, or the intuition is, in the long run, as n gets very, very large, this term will be getting closer and closer to 1 over n. So that suggests strongly that it will have the same kind of convergence status as the series the sum of 1 over n. Now the series sum of 1 over n, of course, is the harmonic series. We know that to be divergent from our earlier work. So we'll be looking at an instance of the second line of that comparison test. So we will compare this to the divergent series, the sum of 1 over n. So we must look at the limit as n goes to infinity of our term, which is n squared plus 1 over n cubed plus 1. You have to divide it by the term you're comparing to, with am over dn. Well, we're comparing to 1 over n, so we're dividing by 1 over n. We're looking at the limit of all of that as n goes to infinity. Well, dividing by 1 over n is the same as multiplying by n. So this is the limit as n goes to infinity of n cubed plus n over n cubed plus 1. Now we want the limit of that sequence. So we should think about the algebra of limits theorem for sequences. It's a limit of a quotient, so we'd like to say it's the quotient of the limits, except we need to prepare it first because the top and bottom are unbounded individually at the moment, but if we divide above and below by n cubed. This can be replaced by 1 plus 1 over n squared by 1 plus 1 over n cubed. So we haven't changed the way we express the fraction, but we haven't changed the whole fraction itself. We've divided above and below by n. So now you can say that this is equal to the quotient of the limits. Which is just 1 over 1, which is just 1. So this is RL. In the language of the test over here, in the notation of the test over here, this is our L. But is L, well, all we have to have for L here is just that it be strictly bigger than 0, which is, of course, 1. So therefore, by the limit comparison test, then, the limit comparison test, our series, it diverges also. Okay. Let's look at another example, which is kind of similar to that. This was a kind of slight twist in it. So this will be example 3. So this time, so decide the non-convergence of this series. So this is sum from, well, let's change the letter for the hell of it. M equals 1 to infinity, 5m minus 2, square root of m to the power 6 minus 4m squared plus 7. Something like this. Okay, this isn't exactly a rational function. It's not exactly a quotient of polynomials, although nearly is, except it's just complicated slightly by we're taking the square root of a polynomial on the bottom. But maybe we could just push ahead and try and apply the same thinking to it. So again, you'd look at the dominant behavior. So looking at the dominant behavior here, this looks like, in vague terms, as m gets really, really large, the top is like acting like 5m. Factor subtracting 2 becomes insignificant when you get really large. And the bottom is looking like the square root of n to the power 6. The minus 4m squared and plus 7 become less and less significant as n gets larger and larger. And of course, the square root of m to the power 6 would be n to the power 3. M cubed. So in total, it's looking like an m over m cubed, which would be 1 over m squared, or a 5 times 1 over m squared, if you will. Constant multiples, constant factors of these things don't affect the convergence or divergence. It's really just looking at how the thing depends on the index. So this looks like 1 over m squared. Okay. Now that, remember, we already know about all of the hyperharmonic series, these series which are the sum of 1 over some power of the index, fixed power of the index. Because we assessed all of those using the integral test. And the sum of 1 over m squared is convergent by the integral test. Rather nice, that image, but I wonder what it is. Is it that phone recharging? I kind of like it. What was it? You know that Christmas movie, It's a Wonderful Life? What did it mean when you heard the bell ringing? An angel has wings. So was that good? Was it? That was an angel going up. Yeah, an angel going up. So it's a good sign. Okay. So where are we going here? We're comparing to 1 over m squared. So again, we should use the limit comparison test. Okay. So we'll look at the limit as m. See, m is the index now, so we should use m. As m goes to infinity, of our term, which is 5m minus 2, over square root of m6 minus 4m squared plus 7. And we want to divide it by the term we're comparing, 1 over m squared. So we want to look at the limit of that. So dividing by m squared, of course, is the same as multiplying on the top by m squared, dividing by 1 over m squared. So this becomes 5m cubed minus 2m squared, all over square root of m6 minus 4m squared plus 4m squared plus 7. Again, you can't quite use the algebra of limits theorem straight away because top and bottom are still unbounded. So you need to divide above and below by the highest power of m that you see. Now don't think that you're seeing m to the power 6, because the m to the power 6 is under square root sign. So the highest power of m you're seeing here is m cubed. So when you divide above and below by m cubed, you get 5 minus 2 over m on the top. Dividing the bottom by m cubed, well, in order to bring the m cubed in underneath the square root, you have to square it. So, and it becomes a m6. So it's, yeah. So it's 1 minus 4 over m to the power 4 plus 7 over m to the power 6, I believe. And now we can say that this is equal to the quotient of the limits. So it's the limits of 5 minus 2 over m divided by the limit as m goes to infinity of the square root of 1 minus 4m4 plus 7 over m6. And yeah, okay, here we'd allow that this, we can say that the 2 over m is converging to 0, the 4 over m4 and the 7 over m are 6. Those are all converging to 0. So this we'll say is converging to 5 over the square root of 1, which is equal to 5. Since 2 over m minus 4 over m4, 7 over m6, these all converge to 0 as m tends to infinity. Technically, I think we need to appeal to we also need to cite the continuity of the square root function here. This kind of points or just kind of looks forward to some of the work we're doing with continuity now in this new chapter, which we'll pick up after Christmas. I won't bother too much about it at the moment, but I'll just put it in here as a remark. We also need to cite the continuity of the square root function. Because we're basically saying that the limit of the square root of something is equal to the square root of the limit of the something. I.e., saying that the limit of the square root of f of x as x tends to a is equal to the square root of the limit of f of x as x tends to a. This kind of operation of interchanging the order of a limiting process applied to a function of something, saying that that's the function of the limiting value, that property is the continuity of the function that we're swapping the order of. So this is the continuity of the square root function. Yeah, but we've just started talking about continuity. We'll be picking that up, talking about that in a lot of detail after Christmas. Of course, it's not angels getting wings, it's you getting Facebook messages, isn't it? Which probably someone here is sending to you. I've figured it out now. Send them a text, make a different noise or something. Okay. It's okay in the or here's one to think. We've still got a few minutes left, so here's one to think about. So what was that? That was 3. What about the sum of 1 over n factorial? Can we handle that one in the same way as we've handled some others? Let's have a think about that for a few minutes. See, look at the other examples we've done today. See if you could fit that into, do it in a similar way to one of the previous examples, and discuss it with your neighbors. See if you get any ideas for it. I'll go through the solution now in a couple of minutes. Are there any other questions or queries in the meantime that anybody wants to ask? You do have your tutorials later today, so do make use of your tutors there. Last minute preparation in. There's our sum over of 1 over n factorial. Now, does this pass the general term test? Yeah, it does. The terms are certainly converging to 0. 1 over n factorial. As n gets larger, n factorial is getting larger without any bounds. So 1 over n factorial is getting smaller, converging to 0. And it does so fairly fast. N factorial increases quite rapidly. Is it doing it fast enough? And we make that judgment by comparing it to something that we know about through other means. So any kind of now, if we suspect convergence here, we'll be looking for a less than or equals. Now this is difficult to handle exactly because all these numbers here are different. Some way we can simplify it in such a way that we are making the fraction larger. It's awkward at the moment because every factor is different. Is there a way I can make them all the same? I could replace them all by 1. Certainly, this term 1 over n factorial is certainly less than 1. That wouldn't help me, though, because 1 isn't the term of a convergent series. If you look at the series, the sum of 1 for every value of the index, that's clearly divergence. It's 1 plus 1 plus 1 plus 1. you want to make sure it's less than something convergent. So, but I could also replace, I could also replace everything by 2 in the same way that I did before. You see, or let's leave that 1 there. So we'll leave the 1 at the end. We won't change that. We won't change 2. But instead of a 3, we'll replace it by 2. And instead of every number, after it, we'll replace them all by 2. So we're making, again, like before in the n to the power n case, we're making the denominator smaller, so we're making the whole fraction larger. So this whole fraction is less than this one. And this one is, again, this is our geometric friend. This is 1 over 2 to the power m minus 1. Because there's m factors there, but one of them is 1, so there's only m minus 1, 2. So that is, so our term is less than the term of a convergent geometric series. So this one, the sum of 1 over 2 to the m minus 1, from m equals 1 to infinity. What does that convert to? Sorry? What does that convert to? 1. Another one. One. 0. This converts to 0. 1. 1? Yeah. Well, when m is 1, see, what does it look like at the beginning? It looks like when m is 1, it's 1 over 2 to the power 0, which is 1 over 1, which is 1. And then you have the half and the quarter and so on. It's 2, yeah, 2. Yeah, so trying to catch up. When we had it before, the sum of 1 over 2 to the m, where m went from 1 to infinity. That was 1. Yeah, this one is 2. Or you can see that because it's you would write this is the sum of a to the r to the m minus 1, where a is equal to 1 and r is equal to a half. So this will have a over 1 minus r, so it'll be 1 over 1 minus a half, which is 1 over half, which is 2. So it does have a limit. It is convergent. So by the comparison test, so is R. So this is, well, a bit scrappy here. This is, finish this sentence. This is convergent by the geometric series test. So the sum of 1 over m factorial from m from 1 to infinity is also convergent by the comparison test, standard comparison. Okay, hope you found that useful and many. So good luck in your preparations for the test tomorrow. I'd advise you to sorry, tomorrow. The next Thursday. Prepare with the mock tests. Look over all the tutorial questions. All the solutions are up on Moodle. Make use of your tutors now this afternoon. And I will be seeing you for another lecture next Wednesday morning. So there's an opportunity for final questions then. Yeah.